Hello, this is the Test 4 review lesson. Test 4 is all about hypothesis testing. Specifically, it's the topics in chapters 8, 9, 11, 12, and 13. For this test, you're going to want to use your calculator, your z-score table, the wording of the final conclusion flowchart, your hypothesis tables worksheet, which contains all the tables that you're going to need except for the z-score table. Use any notes you want. And you may also want to print the Test 4 review sheet, which is in the Test 4 review lesson folder. That review sheet contains the topics you'll want to review as well as a table that summarizes all the different hypothesis tests that we've talked about. First, let's talk about what are we doing in hypothesis testing and why are we doing it. In a hypothesis test, we make a claim about a population parameter, such as a population proportion or mean, or some other parameter. In order to determine for certain if that claim is true, I'd have to go out and interview every single member of my population and then calculate the appropriate population parameter. But that's very difficult, if not impossible, to do. So instead, we go out and select a sample, and based off of that, we collect some data and calculate sample statistics, such as a sample mean or sample proportion. These sample statistics don't prove anything about the population parameter. Instead, they are estimates of whatever it is we're interested in. In hypothesis testing, we determine if that data supports the claim, and if so, just how strong that support is. And based off of that, we can determine if we support the claim or if we do not support the claim. So one thing that you'll have to do is calculate a p-value by hand. Now, throughout many of these different hypothesis tests, we let the calculator do p-values for us. But back in section 8.2, we talked about how to calculate these by hand. We had three different ways of calculating p-values, and it all determined by the form of the alternative hypothesis. If the alternative hypothesis has a less than sign, then we had what we call a left-tailed test, and the p-value is the area to the left of the test statistic, z. If we had a greater than sign, then we had a right-tailed test, and the p-value was the area to the right of the test statistic, z. If we had a not equal to sign in the alternative hypothesis, then we had a two-tailed test, and the p-value is twice the area of the extreme region bounded by z. If z was negative, then the extreme region is to the left. If it's positive, then it's to the right. So you find that appropriate area, take it times 2, and that's your p-value. So a typical test problem is you'll be given alternative hypothesis, the value of the test statistic, you have to find the p-value. There at the bottom is our criteria that we used for coming to our technical conclusion. We reject the null hypothesis if the p-value is less than alpha. We do not reject it if it's greater than alpha. Now, what is a p-value? Well, informally, the p-value is the probability that the sample statistic occurred by chance, assuming the null hypothesis is true. If that p-value is small, meaning we have a small p-value such as less than 0.05, then that's an indication that my assumption of the null hypothesis is incorrect, and so I reject it. That's how we come to that technical conclusion if we have a small p-value. Now, in all these different sections, we had different formulas for calculating the test statistic, and we didn't really use many of them because most of them were very difficult, but we did have one that from section 8.3 for calculating the test statistic for a claim about a proportion. Here was the formula. You had p hat, which is your sample proportion, p naught is the population proportion that's used in the null hypothesis, q naught is 1 minus p naught, and n is your sample size. The point of reviewing this is just to remind ourselves that these sample statistics are all calculated using formulas and using the sample statistics and other numbers that we see. Now, all of our different hypothesis tests had different requirements that had to be met. If these requirements were not met, then we do not get valid results. We're going to talk about requirements for a couple of those different types of claims. Here's the requirements for a claim about a proportion. First, the sample must be random. That's always a requirement. Second, the conditions for a binomial distribution are satisfied. There were 4 different conditions there, but the important one is the last one, that all of our outcomes fall into 2 different categories, success and failure. The third one is also important. The conditions NP0 greater than 5 and NQ0 greater than 5 are both satisfied. This is important because if I have a real small sample size, like N is maybe only 5 or 10 or 15, I may not meet this requirement, and so I won't be able to use that data to test my claim. Now, the requirements for testing a claim about a single population mean are these. First, the sample must be random, and then second, either the population is normally distributed or N is greater than 30. The second one there is the important one, because if I have got a small sample size, like only 10 or 20, I may not be able to use this test, there are these formulas, if my population is not normally distributed. Next, I want to review all the different types of hypothesis tests we've done. We've talked about 10 different ones. These are all summarized on that Test 4 review worksheet. I just want to go over them quickly and remind ourselves how to do it and what the calculator commands are. So the first test was a test about a single population proportion. The calculator command was option 5, the 1 proportion z test. That asks you for P0, which is the proportion used in the null hypothesis. X is the number of successes, and N is the sample size. Now remember, X, the number of successes, has to be a whole number. Some problems, they don't give you number of successes, you have to calculate it. Remember, if you calculate it, you always have to round that off to a whole number. The second test is a test about a single population mean. There the command is option 2, simply called the t-test. It asks for mu0, the mean in the null hypothesis. X bar and Sx are the sample mean and the sample standard deviation, and N is the sample size. Test 3 is where we are comparing 2 different population proportions. Here we have data from 2 independent samples that come from 2 different populations. The command is option 6, the 2 proportion z test, and it asks for x1, n1, x2, n2. X1 and 2 are the number of successes in samples 1 and 2. N1 and N2 are the number of the sample sizes of sample 1 and sample 2. Now remember, when you enter these into your calculator, your X1, N1 have to correspond to the population that's defined in the P1, the population proportion P1. Likewise, X2 and N2 have to correspond to the population in P2. Number 4 is similar, except we're comparing 2 population means, and there the command is option 4, the 2 sample t-test, and that'll ask you for x bar 1 and 2, Sx 1 and 2, and N1 and 2. Those are our sample means, sample standard deviations, and sample sizes. And then you always choose that option pooled no. Number 5 is the paired t-test. And with paired t-tests, we are to some extent comparing 2 populations, but the difference here is that our data are not independent. Our data come in matched pairs from 2 different measurements. Our parameter here is called mu sub d. The subscript d it means that it's a difference. Mu, it's the mean. Specifically, mu sub d is the mean of the first measurement minus the second measurement. And then the claim is about mu sub d. Maybe it's that mu sub d equals 0 or is greater than 0 or less than 0 or something to that extent. Now, doing this on our calculator was a little more complicated. We had to put our first measurements in L1, the second measurements in L2, and then we enter the command L1 minus L2 store at L3. That list L3 then contains values of the differences, and we use a t-test to test the claim about mu sub d. Number 6 is what we call a goodness of fit test. That type of test, we are testing if observed data quote-unquote fit a given distribution. Our data is categorized into several different categories, and what we are given is the observed frequency of each of those individual categories. So the example we did in class was that the distribution of the loaded die fits the distribution of the fair die. In mathematical notation, our null hypothesis was that P1, the proportion of 1s, equaled P2, the proportion of 2s, all equal 1/6. The alternative really wasn't terribly important, but is a statement that at least one of those proportions is not as claimed. And this one we calculate our test statistic by hand. We set up this table. We calculated the expected frequencies, which are simply the sum of the observed frequencies times the claimed proportions. And then in the end we took the observed minus the expected, squared it, divided by the expected, added it up, and we got our chi-square test statistic. And then we used a traditional method to come to our technical conclusion. We compared the test statistic to a critical value, which comes from table A4, which is on that hypothesis testing tables worksheet. If the chi-squared was greater than the critical value, then we reject the null hypothesis. If chi-squared is less than the critical value, then we do not reject it. And remember, the degrees of freedom is the number of categories minus 1. Some calculators have a built-in command for doing this type of test. If you have it, you enter the observed values in L1, the expected values in L2. You choose the option D, chi-squared goodness of fit test, and it'll ask for DF, which is the number of categories minus 1. Test number 7 is what we call contingency tables. In a contingency table, we have two different variables. One we call the column variable, the other is called the row variable, and our data are observed frequencies of those different categories. So the example we did in class was we had the color of motorcycle helmets, either black, white, or yellow and orange, and then whether the person was not injured or killed. So we have our column variables are the color of the helmet, the row variables were either injured or not. The claim in a contingency table is that the row and the column variables are independent, meaning that the value of one has no effect on the value of the other. The null hypothesis is this claim, and this is what we call a test of independence, because we're testing if things are independent or not. Now this is one that we could do on our calculator. We entered the observed frequencies as a matrix, and the command there was stat test, option C, the chi-squared test. Test number 8 is what we called ANOVA, which stood for analysis of variation. In ANOVA test, we are claiming that two or more populations have the same mean. For this one we had several different parameters, one parameter for each of our different populations, and then our claim, which is the same as the null hypothesis, that mu1 equals mu2 equals mu3 equals mu4. In other words, we're claiming that those different population means are all equal. The alternative hypothesis was that at least one of those was different, but that's really not terribly important in this type of test. And this is one that we did strictly on our calculator. We entered the data in lists L1, L2, up to however many lists of data we had, and we chose the option H, ANOVA. That pasted the ANOVA command back at the blank home screen, and then we entered the names of the lists containing the data, L1, L2, etc. And then that gave us a p-value. The test number 9 was the sign test. In a sign test, we're testing a claim about a population median. Our data is of the form of a bunch of plus and minus signs. To do that, we let x be the number of times the less frequent sign occurs, and n equal the total number of positive and negative signs combined. If n was less than 25, then the test statistic is x. If n is greater than 25, we didn't get into that case. Now this one we did a traditional method for coming to our technical conclusion. Our critical value comes from this table A7. Along the left hand side you see n, across the top you see alpha, with different values of alpha, and below those either one tail or two tail. And whether you use the one tail or two tail depends on what type of inequality you have in your alternative hypothesis. If you have a not equal to sign, then it's a two-tail test. If it has a less than sign or a greater than sign, then it's a one-tail test. So typically we're going to be using alpha as 0.05, so we'll use either the third or the fourth column. Whether you use the third or the fourth depends on whether you have a one-tailed or two-tailed. The criteria for coming to the technical conclusion is that we reject the null hypothesis if x is less than or equal to the critical value, and we do not reject the null hypothesis otherwise. The last test is what we call the runs test, and in this type of test we are testing the claim that a sequence of data is arranged randomly. Our data values come in two types, like male, female, heads, tails, plus, minus. Our hypotheses, the null is that the data are in a random sequence. The alternative is that the data are not in a random sequence. To do this, we let n1 be the number of elements of the first type, n2 was the number of elements of the second type, and g was equal to the number of runs. Now it doesn't matter which one you call the first type, which you call the second type. You could switch them around and you get the same thing in the end. We used a traditional method for doing this type of test. The critical values come from table A10, which are on that hypothesis testing tables worksheet. And the criteria there is that we reject the null hypothesis if g is less than or equal to the smaller of the two critical values, or g is greater than or equal to the larger of the two critical values. And we do not reject the null hypothesis otherwise. So that's it for the review. The test will consist of basically one problem of each of those different types of hypothesis tests, plus maybe a few other interpretation type questions. One quick reminder, don't forget to do the final project, which involves an application of one of these hypothesis tests, and there's more information on that on the syllabus.